Hi, people watching this video. Hey. Okay, we are filling out a review for this chapter. They decided to do this today rather than Monday. We're filling out a probability review, and this is a blue sheet. And I'm giving this to you, and we're going to fill it out together, and you can use this on your test. Okay, so there's that. There are a couple things, like maybe one thing I know for sure on here that is not something that we talked about. A circular permutation, you can cross him off. We talk about him in geometry, but we haven't had any of those this time. So you can go ahead and cross off circular permutation because you won't have any questions on that. And this will just, I'll give you some examples. We'll write down important information, all that good stuff, okay? Fundamental counting principle, I'm going to start him with sectioning this box off just a little bit. I'm going to split him in half like that. I'm going to split him in half, okay? Just because the fundamental counting principle, like sometimes you'll have questions on the fundamental counting principle and one of them is like very different than the other, but you use the fundamental counting principle no matter what. Okay, so let me start with the example. And let's do this. I'm going to do the 4 shirts, 3 pants, 6 pairs shoes. And then I'm going to say how many outfits. You guys know what this is? You know what you're doing now? Okay, now that I give you the example, you're like, yeah, now I know what to do. So before we solve that, what's the equation? What do we do when we're calculating this? You multiply them all together. So the number of ways is like n1 times n2 times n3 and so on and so forth. We keep multiplying all of those options together until we get the answer, whatever. Important information, n to whatever power, those are just the number of options of each. Okay, so if you need to write that down, whatever that is. N to whatever subscript is just the number of options that you have. Okay, now if there's anything on here that you like doesn't make sense, like if you don't know what n question mark equals number of options, write it down in your own terms. That way you can understand it when you go to write this down on the test. So if what I'm writing down doesn't make sense to you, just write it in your own terms or ask me and I'll explain it in a different way, and then you can write it down that way so that it makes sense to you. Does that make sense?
Does that equation say
n1 times n2 times n3. My times don't look very timesy. So n1 times n2 times n3. Good question. Okay. All right. So how many different outfits can we have? We take 4 times 3 times 6, and that's 12 times 6, or like 72 or something. 72 different outfits. Yeah, something like that. Okay. All right. Moving on down below. Fundamental counting principle, same equation, same information, but this looks a little bit different in the way that the example is worded. You still use the fundamental counting principle, but it's just a little bit different wording. So, and these were the ones that we saw on the homework assignment. So, how many passwords? Yes, repeat. 4 characters. I'm going to say 4 digits. We'll just do digits, not characters. Characters would be like numbers as well. Okay. How many passwords? If we can repeat, and it has to be 4 digits long. Okay. This is a fundamental counting principle, but it is very different example than what the outfits one was. That's why I do 2 different examples, because they're just, it's like they're very different examples, but they're the same formula. Okay. So 4 digits. 1, 2, 3, 4, okay, and we're just doing digits. So how many numbers could go in the first spot? 10, right? Because 0 through, I'm going to do a different color. 0 through 9 is 10 digits. If we can repeat, it would be 10, 10, 10, 10 all the way through. 10 times itself 4 times is 10 to the 4th power, or 1 with 4 zeros, right? Or 10,000 different passwords. Does that make sense? And then if they ask for probability, like, what's the probability of somebody guessing it right? It would be 1 out of 100,000 or 10,000, whatever it is, right? Okay. What if you can't repeat?
Then just 10, 9, 8, 7.
10, 9, 8, 7. What if we can now include, like, letters also?
When you add them.
like 36.
Like 36, right? There's 26 letters, and 10 numbers, so that would be 36, 36, 36, 36. Does that make sense? If you can include letters as well. Okay, what?
You're not gonna do that with those,
I don't know. I don't know. Just pay attention to how many things could go in each spot, right? Okay, if I say, let's say I say this has to be a 1 or a 2. Now let's say a 1 or a 0. We have to lead with a 1 or a 0. Now, how many numbers could go in that spot?
2.
Only 2 numbers can go in that spot. It's either a 1 or a 0, right? Does that make sense? So you just pay attention to how many options could be in each slot. I really, really suggest that when they say passwords, you write out the 4 blanks. It just helps to organize your thought process a lot better. Make sense? Yeah? Okay, so I'm going to erase that so that people don't get confused with that. Okay? But just pay attention to what I'm asking for and all that good stuff. Okay? All right, now we have permutations, combinations. Let's write some important information down. Permutation is NPR. Combination is NCR. They have equations, but I don't make you write them down because you will never not have your calculator to do it for you. So there is that. Okay? NPR, NCR. There he is. What is N and R? And I'm going to do this for each one of them. Same thing. N equals the total. What's R?
Number choosing.
R equals the number choosing. Okay, N equals total, R equals the number choosing. Okay, good. All right, I'm going to separate permutation example into 2. I won't do this for every single one of them, so sorry. But I'm going to separate permutation into 2 just because there's 2 different examples that I want to talk about. So the first one is how many batting orders with 9 players? 9 people can bat at a time, right? I have that number right? 9 people. Okay. How many batting orders with 9 players? Okay. How many batting orders can you do with 9 players? Okay, now, you can do this 2 different ways, okay? You can do it with the blanks, like 1, 2, 3, 4, 5, 6, 7, 8, 9, right? Okay, where you do how many people could be in that first spot or first batter, that would be 9. Once that person's chosen, how many people can be in the second spot, that would be 8, 7, 6, 5, 4, 3, 2, 1, right? Which is equivalent to 9 factorial. You just type that into your calculator. Or if we do this as a permutation, okay, the order in which I choose you matters, right? Like first batter is not the same thing as second batter. Like you're supposed to, I didn't know this about baseball and softball and stuff, but every third or fourth person you're supposed to have a heavy hitter because it's supposed to bring everybody home. There's a strategic order to where you put people in the batting order. So order does matter. It's a permutation, okay? So, but if I do this as a permutation and I type it in, it would be 9P9, right? You have 9 total and you're choosing all 9 of them, right? 9P9 is the same thing as 9 factorial. Writing it out like that. Those 2 things mean the same thing. You can do either 9P9 or 9 factorial, it doesn't matter. And if that's the case, what do you get? A big, huge number. Real big. 362,880. Perfect. That's how many different batting orders. If I just have 9 people, that's how many different batting orders I could do. Lots and lots and lots. All right, now let's go to the standard one. What do you want to do, for example? Do we want to do students? Do we want to do books? Do we want to do puppies? Do we want to, puppies, I know, but puppies would, we can do puppies. Okay, let's do puppies. Okay, puppies. 10, let's do 12 puppies. In a race. There's 12 puppies in a race. How many ways? 4. First, second, third place. Okay, how many ways can I choose a first, second, and third place? Okay, does the order in which I choose them matter?
Yes.
Yeah, if you got third, or if you got first, you don't want me to put you in third place. That would be really bad. Okay, so this is a permutation because order does matter, right? And so this would be 12p3, right? Because we're choosing 3 of them. Not 3p12, but 12p3. And if you try to type it in as 3p12, it will say either 0 or like error or something where it doesn't like you very much, okay? What do you get? How many different ways? 1320? 1320. Okay. All right. So there's the standard like permutation example that that like makes sense that that's a permutation. One more thing that maybe we need to add to permutation is that order matters. And then this one is order does not matter. Make sense? And the way that I remember that is permutation is president. And president starts with a P. And when you're doing president, vice president, secretary, the order does matter, right? Like we would have a very different thing probably going on if Kamala Harris would be president versus Joe Biden, right? Like we might have something different happening. I don't know, maybe not. Whatever. Anyway, so there's that, right? If they were chosen in a different order, we would have a different system, so order does matter. Combination is committee. And in a committee, order doesn't matter. I can draw your names one way and then switch them around, draw them another way. You're all going to be on the same committee. It doesn't matter. Okay? So you have the same job. All right? Good? Let's do a combination. So we do puppies again?
No. Sorry. We
Can
should
you
do
do
turtles.
Turtles?
Yeah.
Okay, sure. She wants a turtle race. Okay. All right, we'll do a turtle race. That's fine. Okay, can I scroll over to my example?
Yeah.
Turtle race. We'll do 12 turtles.
Turtle.
12 turtles.
Yeah.
12 turtles, I'll say in race. I abbreviate a lot. Do you guys understand my abbreviation stuff? 12 turtles in a race. How many ways? How many ways? In race. Races. In race. Whatever. In race. Whatever. How many ways? Oh, heavens. Ways to choose top 3. Now, if I'm choosing top 3, I am not looking at the place that they're in. I'm only saying, are you in the top 3 or are you not in the top 3, right? So if I'm just saying top 3, it doesn't matter if you got first or third, you are in the top 3 no matter what. Like you're going on to the next, like whatever, right? If you make the top 3, you go on to the next round. It doesn't matter if you got third or first. You made the top 3, you're going to the next round, right? Whatever. Okay? So order does not matter. So this would be 12C3. And that is more or less than 1320. Less, because we've divided out the repeats. So less. 220. Perfect. 220 different ways that I can choose those 3 turtles out of 12. Perfect. Not too bad. Any questions so far? Are we doing okay? Yeah. Okay. All right. Here we go. Moving on. Permutation. Oh, shoot. I got ahead of myself. We separated the permutation 1 into 2. Because I give you a space for that right here.
Now we don't have to do those.
Nah. So we don't have to do n equals r, right? N equals r would be like choosing 9 when you have 9, right? Like the batting order example that I just gave. Sorry, guys. I should have put that down below. Anyway. So you can cross it out like it's like that's what it is. I just drew an arrow because that's what he is, right? So you don't have to do that line. I got ahead of myself. Sorry. Anywho. Okay. But we do have to do permutation with repetition, so don't cross him out. Right? Just cross the other one out. So n equals r, permutation where n equals r, that's 9 equals 9, np9, or 9p9. Are we okay so far? I kind of confused you a little bit, all right? Okay, let's do permutation with repetition. So this is the ones where we did like Ellie's name, right? Okay, where you have repeating letters, okay, or things that repeat, right? Okay, let's do... If I do numbers, is it going to really confuse you?
Yeah.
Like a phone number?
No.
Don't use the phone numbers.
You have to confuse me, otherwise we're never gonna.
Whoa, Addie. Not all because
never
we're on
gonna
that
be
level
smarter.
yet.
Okay.
All of us
All
are
right.
on that level.
Permutation with repetition. All right. So the formula for repetition, or the formula for permutation with repetition, is n factorial over, I don't know if they use these variables the same or not. I think they did like n's on the bottom. But I do r1 factorial times r2 factorial times r3 factorial, etc., right? And you just keep going for the number of repeats that you have, right? So however many that you have repeating. Do you guys even have home phone numbers anymore?
Yeah.
Like 756? Somebody give me one.
756.
What do you got?
756-3656.
Oh, that's a good one.
I'm calling
That's
it.
good. I like it. Okay, we're gonna do Caleb's number. All right, so let's label n. N is total, and r whatever, r question mark, is the number of times each repeats. Okay. Now there's a reason why I want to do numbers. I'll show you why. 756 what?
3656.
3656. Okay. 7563656. Holy crap! That's a little. That's like yeah. That's a good repeating one. I like it. I like it a lot. Okay, so here's what we're doing. We're taking Caleb's phone number and we're chopping it up and we're putting each one of those on a slip of paper, right? And I'm going to put each one of those numbers into a hat and I want to draw them out and see if they write out his phone number exactly, right? Like maybe instead it would do something weird and it comes out a weird way, but I want to know like the chances of it pulling out that exactly. So, how many ways, or I'm going to say how many phone numbers can we make with these numbers? How many different phone numbers can we make with these numbers? Now, notice that Caleb doesn't have like an 8 in his phone number. So we're not using any 8s. We're only using the numbers of his phone number and seeing how many from there we can create, right? Okay. So, how many phone numbers can we make with the numbers of his phone number, right? So he has 7. You have 7 numbers total. So n is 7, right? Okay. So we do 7 factorial on the top. Okay. Now, he has 2 numbers that repeat, right? They are like 5 and 6, right? Okay. So 5 and 6 repeats. So here's why I wanted to do numbers. What numbers go on the bottom of the 7? Not 5 and 6.
2.
How many times does the 5 repeat?
2.
5 repeats.
2 and 2.
5 repeats
2 and 3.
2 times. 6 repeats
3 times. Sorry, I didn't.
3 times. So you don't put 5 and 6 on the bottom. You put 2 and 3 on the bottom. So we have 2 factorial times 3 factorial. Right?
Okay.
Does that make sense?
Yeah.
That's why I wanted to do numbers instead of letters. Okay. So if they give you numbers, it's the number of times it repeats. It's not the actual number. All right. So if you plug this into your calculator, you need to make sure you put parentheses around the bottom, or we can just figure out what that is. We have 7 factorial. 2 factorial is 2 times 1, right? 2 times 1. 3 factorial is 3 times 2 times 1. So can you simplify that bottom so we don't have to like work real hard in our calculator? What's 2 times 1 times 3 times 2 times 1? 12, right? So this is 7 factorial divided by 12. That's a lot easier to type in than, whatever. 7 factorial divided by 12, what is that?
I got 420, but I have
420.
420, okay, perfect. 420 different numbers could be created with Caleb's number. Now, if he didn't have any letters that repeated, no letters that repeat, can we make more numbers or less numbers than 420?
More.
We can make more, right? Because we have more letters to use, right? Or numbers to use, I mean. Okay? Was that confusing? No. Okay, not too bad. All right, now we have just a couple left. Independent, dependent, because these ones kind of go fast. Those 2 are together. And independent, dependent is when you are multiplying or adding. Independent, dependent. Multiplying. This is when you're multiplying probabilities. And these are the and statements. Okay? Multiplying, these are the and statements. I'm going to go down here to mutually exclusive versus inclusive. These are the or statements. This is when you are adding. Okay? Multiplying, adding, okay? Some important information. I'm going to put little stars up here. Star. You are multiplying. If you are choosing more than 1, right? You're choosing more than 1, you're multiplying. If you are only choosing, is that mine? Is that my dinger going off right there? Okay. Ah, it's a group text. Yeah. Okay, choosing more than 1, only choosing 1, that type of thing. There he is. Multiplying, adding. Oh no. Oh no, she's fine. All right, are you good? Good to go? Okay. All right. We're gonna go fast. Independent, dependent. If you are multiplying, a lot of times what you will have with independent, dependent is this one will say with replace, and the other one will say no replace. Does that make sense? With replace, no replace. I forgot what my headings were. Equation. Equation, you're multiplying. Something times something. This is like a fraction times another fraction, right? Good? Make sense? Okay, fraction times another fraction. And when you have no replace, a lot of times you will subtract from the bottom. Okay, you'll subtract from the bottom. And you maybe subtract from the top. If, what happens? When do you subtract from the top number also? If you're looking for 2 of the same, like 2 aces or 2 queens or whatever. If 2 of the same. Does that make sense? Do you understand what I'm saying by that? If you don't, you can tell me. So like let's say I'm drawing aces, right? There are 4 aces out of 52. But then the second time, if I'm not replacing, now there are only 3 aces out of 51. I subtract 1 from the top number also, right? Not only does the bottom number change, but the top number does also. I don't really have any important information for the other one. Okay, so let's do some examples. Should we do some cards? Or what would you like to do? Cards? Sure. Do we know cards? Do you know your cards? Kinda? Not really? Not really? Okay. We'll do some easy cards. We'll do some like aces and stuff or whatever. Let's do probability of, I don't know, a 7 and then a king. And a probability of 7 and then a king. Except this one is yes, replace. And this is no replace.
Are you writing this in the second to last box?
Second to last box. I should have moved him down a little ways because we're going to solve it over. You can take up that whole box to write that information down because we're going to solve it over. I thought we had to have a room to solve it. Anyway, whatever. Seven and then a king. Yes, replace, no replace. We'll do these both at the same time. Something times something. Something times something. How many 7s do we have? 4 7s out of 52. 4 7s out of 52. How many kings do we have? 4, and we're out of 52 because we are yes replacing. Okay, how many kings do we have in the second one? Do we have to subtract 1? Is it 3 or 4?
3.
There's still 4 kings in there because we drew a 7, right? If we were doing 2 of the same, then we would subtract, okay? But this one's 4 out of 51. Okay, reduce beforehand. 4 out of 52 is 1 over 13. So 1 over 13 and 1 over 13. 1 times 1 is 1. 13 times 13 is 169. 1 out over 169. Whatever that is a decimal. Okay, on the test where I don't specify what to give me the answer in, I'll take anything. 1 over 169, I'll take it as a decimal, I'll take it whatever. If you're doing 2 different ones, right? Right? Because we're drawing a 7, and then the next time we're drawing a king. So I say, like, the second time around, how many kings are left in there? Well, it's still 4, because we drew 7 first, right? If we were doing a king and then another king, the second time we draw a king, we didn't replace back in there, we only have 3 kings left. Right. Okay. 4 out of 52 is 1 over 13. 4 over 51, I don't think reduces. No, it doesn't. Okay, so it is 4 over 663. Did I do that right? Yep. Okay, there he is. Okay, couple more. When did we get out of here?
35.
35. Okay, so we got some time. Right? Am I boring you yet? Are we doing okay? Yes. Yes. You can be truthful. I don't care. Adding. Mutually exclusive. What does exclusive mean? Important information. Exclusive. What does exclusive mean versus inclusive? If you exclude something, it's not in your group, right? Like if I'm in a group of people and we exclude Jackson, that means he's not a part of our group, right? He's not a part of our group. So what does it mean to exclude something if things are exclusive?
Not involved.
Not in both categories. Not both categories. Like football, volleyball. Can you be a football player and a volleyball player at the same time? Nope, not gonna happen, right? Unless you're playing like club volleyball and you want to play football, whatever. But anyway, we're talking about just the fall sports, football, volleyball. Can't do the same, right? Inclusive, yes, can be both. Example. Basketball, football. Sure. Can you play both? Not at the same time, I mean, but basketball or football. Can you be a basketball player and a football player? Not at the same time, I mean, like whatever, but you can both play basketball and football, right? Okay. Good? Makes sense?
Good one was.
Do we have volleyball players? Yeah, we have volleyball players. Okay, let's just do those categories. Let's do football or volleyball. Okay, so in this class, we have 17 people in here. Well, it will include the people who are gone. So let's do the probability of choosing one person and having them be a football or a volleyball player. I should have written that bigger. Anyway, probability of a basketball or a football player. Okay. Oh, heavens. I shouldn't have put that over there. I should have put that in the third box. Crap. Can I move it over? Are you going to kill me? Sorry.
It's fine.
Sorry. You can switch these two boxes around. That's fine. Yeah, that's fine. I'm going to move it over. Because one more thing I'm going to add. One more thing I'm going to add is that here you're just adding, blah, 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 adding things together when they are exclusive. But if they're inclusive and you have people in each category, you have to subtract out the middle people. These are who is in both. Who is both categories. That's who is in both categories. Has to be subtracted out because they are only one person, but you're counting them twice. Make sense? Good? Perfect. There you go. Okay. Football, volleyball. I'm going to draw a Venn diagram. Can I do that? Football, volley, ball. Here we go. This is basketball, football. Okay. Okay. Are we doing okay? Do I need to zoom out? Are we all right? How many football players do we have in here? 1, 2, 3, 4. 4. Who's missing? TJ and Michelle and Molly. Okay. So just TJ is missing. So 4 football players. How many volleyball players? 4 also? Michelle, Lily, and then you two over there. Okay. So 4 and 4. And nobody's both, so we're going to cancel out the middle. So we would have 4 out of 17, I think there's in here. Plus 4 out of 17. So I would have an 8 out of 17, because you don't add the bottom numbers together. 8 out of 17 chance of choosing. If I randomly come in here and choose one person, I have an 8 out of 17, or about a little less than 50% chance of choosing either a football player or a volleyball player in here, right? Okay. Basketball people. I don't know who's basketball people. 6. Basketball. 1, 2. 3,
Teachers, a reminder, down slips.
Ugh.
Will be
4,
issued today by
5,
noon. Please have all down slips turned in by
6, 7. Because is Michelle basketball?
No.
Oh, okay, never mind. No, so 6. So 6. Okay, so 6 basketball people. Okay. Oh, heavens. Football is 4, right? Okay, but how many of the football players are also basketball players? 3, right? The only one that's not is Jackson. Okay. So 6 out of 17 plus 4 out of 17, but then we have to minus the 3 out of 17 because you 3 boys are only one person and we're counting you twice. Heaven forbid we have 2 of you, right? Ha. So that is 7 out of 17. Okay, so we have to subtract that one person out, so 7 out of 17. Makes sense? You can be in both categories, so you have to subtract them out. Okay, last one. I'm going to do a little Venn diagram here, or a table here. This is conditional probability. Conditional probability. I'll do a couple examples. Okay. Good. Okay. Go back over conditional probabilities is given something happens. These are the given ones, right? Like the probability of choosing a person who's positive for cancer given that they actually have cancer or given that they don't have cancer, whatever, one of those, right? Sometimes instead of using the word given, they will use if instead. Sometimes they will use the word if instead. Okay, so if you see the word if or you see the word given, those two things are going to be conditions. It's like under the certain condition, right? We're not talking about everybody. We're only talking about these people, right? We're only talking about these people. Okay, good? Yes? What category should we do? I'm going to do a table thing here. Let's not do cancer, right?
Or drugs.
What? What?
No,
We could do boy, girl. We could do, I don't know.
Ice cream flavors.
But we need two.
Chocolate or vanilla.
Okay, chocolate or vanilla. And then we'll do, no, because we have to have 2 other things.
Strawberry.
No. No, like 2 categories and 2 other categories.
Just do drugs.
We'll just do drugs. We'll just make up numbers. We'll do chocolate, vanilla. Chocolate, vanilla, and we'll do juniors and seniors. Chocolate, vanilla, junior, seniors. Okay. How many total juniors should we do here?
10.
What? Total juniors? Let's do like 23. Seniors? How many's in the senior class? 22. Okay, cool. So that means total we have 45. That's That's really good. Okay. All right, how many juniors like chocolate out of the 23?
10.
10. So that means 13 like vanilla. Okay, seniors. How many seniors like chocolate?
2.
2 seniors like chocolate? That's it? What?
5.
4, 5, I don't know.
Let's do
7.
8.
8.
8 sounds like a good
10.
Is chocolate better than vanilla or worse?
No.
Chocolate's
Well,
better.
I always get twisted, so
vanilla
I
is
can't
try.
decide.
Okay, vote right now. Chocolate, raise your hand.
Oh, this is really hard. I
Vanilla?
Like most chocolate.
Vanilla? Okay, we're split. So we got more vanillas than chocolate. All right, so let's do like 5 and 17. Should we do that? Okay. I thought we were more chocolate heavy than vanilla. But anyway, we're more vanilla heavy. We're more vanilla heavy. So chocolate's 15 and then 30. I'm in the chocolate boat, folks. There's no chocolate that's bad chocolate. But vanilla, you're like, I don't know if it's going to be a good vanilla or bad vanilla. Okay, so let's do some examples.
Yeah.
Example, we'll do a couple of these. So probability of chocolate given senior. Let's do probability of senior given chocolate. Let's do probability of vanilla given junior. And probability of junior given vanilla. How about that? I don't know why I did vanilla V. Okay, we'll solve each one of those. These are not very long examples. Fraction, 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 fraction. Okay. All right. Do you guys see this little line right here? We know that means given, right? Okay, that little line up and down. So the first one, probably of chocolate given senior. So we're not looking at everybody. We're not looking at all 45 of you. We're only looking at the
5 out of
Seniors.
seniors. We're only looking at the seniors. We start with this number. So seniors, there is 22 of you. And how many of those people like chocolate? 5. So 5 out of 22, whatever that is. We'll just leave it 5 out of 22. We'll just leave it like that. Okay? 5 out of 22. Okay, now if I flip them around, does it become 22 over 5?
No.
Nope. It becomes, so we're only looking at the chocolate people now. Who's the chocolate people? 15. And how many of those are seniors? Only 5. Which is so sad, I know. All right.
Wait, what?
Third one. So 5 out of 15. Because of the chocolate people, only 5 of them are seniors. Okay, the third one. We're only looking at the juniors, which is 23. Of those 23, how many like vanilla? 13. 13 out of 23. Now, given vanilla, we're only looking at the vanilla people. How many are vanilla? 30. And of those people, who are juniors? 13. Is that right?
Yeah, vanilla. 13.
Yeah.
There's 30 vanilla people, and then out of those 30 people, there's only 13 of juniors.
Yeah, you're right. All right. Okay, happy with that? Okay. All right, on the homework assignment, these questions were kind of hard because they didn't give you the table. If you do the table, it's easy. Yeah. Oh, shoot. Okay, yeah. You should have just asked me that ahead of time.
Can I also have another sheet?
Sure. Anybody else need an extra sheet? A couple copies extra, whatever. Okay, this is a long, bye people in the video. This is a long video.